Hi, my name is Kate Penny. I do cryptography research with Dr. Mustafa Atisi at Western Kentucky University, and today I'll be presenting our latest project, finding the information rate of secret sharing schemes using decomposition. So to begin, we're going to have to introduce the concept of keys, which are used to encrypt and decrypt messages in a crypto system. In this basic Caesar cipher below, we're going to encrypt the text hello with a key of 3, and in the Caesar cipher that means moving each letter of the message up 3 slots in the alphabet. And when our receiver receives the encrypted message, he's also going to have the key, and he's going to use that to reverse the encryption or decrypt the text. There are some situations in which we don't want a single person to be able to decrypt the message. Think about missile launch rooms. It always requires 2 people to turn the key to launch the missile. That's because we don't want to entrust all the power to just one person. To implement this kind of system in a crypto system, we're going to form what's called a secret sharing scheme. So we have our key of 3 here as an example, and we want to split it in between 2 people so that we require both of them to be able to decrypt the message. Well, we're going to split the key into what are called partial keys. A partial key of 1 will go to participant 1, and a partial key of 2 will go to participant 2. And now the participants are going to be able to combine their partial keys to get the whole key back and decrypt the message. We form what's called an authorized set with participant 1 and 2. This defines them as being able to come together and combine their partial keys to form the whole key. We can also have secret sharing schemes of more than one authorized set. So in this example, we're going to define 1 and 2 as being able to form a whole key, and 2 and 3 as being able to form a whole key. Only these groups should be able to decrypt the message. If we take our key of 3, we can distribute them as partial keys among 1, 2, and 3, so that 1 and 2 are able to form 3, and 2 and 3 are able to form 3. But 1 and 3 are not able to form the whole key. This makes it a very secure information distribution system. We can represent secret sharing schemes as monotone circuits. So for example, with our authorized groups of 1 and 2, and 2 and 3, we can define 1 and 2 being able to come together, or 2 and 3 coming together to form the whole key. We can also represent secret sharing schemes as graphs. So with our basic example of participants 1 and 2 as an authorized set, we make participant 1 a vertex and participant 2 a vertex, and the edge between them represents their combining of partial keys. With our example of 1 and 2 and 2 and 3 as authorized sets, we get something like this, a bipartite graph. In general, we compute the efficiency and security of a secret sharing scheme using its information rate. For a single participant, the information rate of that participant is the number of bits in the key and the number of bits that participant gets in shares. The information rate of the entire scheme is the minimum of all of those across all participants. Ideally, this number is high because we want the number of bits the participant gets in shares to not exceed the number of bits in the key. That way the participant gets less and less partial keys and knows less of the whole key, making the system more secure. But we can't get an information rate higher than 1, because the number of bits a participant gets, or the number of bits in the key, cannot exceed the number of bits a participant gets. It's pretty easy to look at a representation of a secret sharing scheme as a circuit and find the information rate of it. For this example, our authorized sets are 1 and 2, 2 and 3, and 3 and 4. And the number of bits in the key are represented as the wires going to each participant. So 1 has 1 wire going to it, it gets 1 bit of shares, and our key is 1 bit long, presumably. 2 gets 2 shares, and our key is 1 bit long, so its information rate is 1/2. 3 is also 1/2, and 4 is 1. The minimum of all these values, or the total information rate, is 1/2. It's about the same principle when we're looking at the information rate of a secret sharing scheme in graph form. The number of bits of shares going to a participant are just the number of lines it is connected to, or edges it is connected to. And so we get similar results. 2 has 2 edges from it, 3 has 2 edges from it, 1 and 4 both have 1 edge from it. And the minimum of all these information rates is 1/2, so the total information rate of the scheme is, again, 1/2. Now, secret sharing schemes that can be represented as complete multipartite graphs have very interesting properties in that their information rate is always 1. And this has to do with how we distribute the key among this graph, and we don't have time to prove it right now, but we can use this property to essentially decompose a secret sharing scheme in graph form into complete multipartite subgraphs. And each of these decompositions we will distribute a key of 1 bit, And based on how that key is distributed in the decomposition, we may be able to obtain a higher information rate. Just to provide some notation for this process, we're going to look at a book definition of it called L decomposition and construction. And the key takeaway from this section is that we're going to define R of I as the number of times a participant I occurs in a decomposition or a covering. And we're going to define L as the number of coverings or decomposition schemes there are, because that's going to be the number of bits in our key. This process is really best illustrated with an example. So we're going to have our authorized sets of 1, 2, 2 and 3, and 3 and 4 again. We're going to decompose that into a complete bipartite graph 1, 2, and 3, plus a complete bipartite graph 4 and 3. And another decomposition would be 4, 3, and 2 in a bipartite graph, and 1 and 2 in a complete bipartite graph. So we have two decompositions, so our key is bit length 2. And among all of these, participant 1 receives 2 partial shares, 1 here, 1 here. Participant 2 and participant 3 both receive 3 partial shares. 3 is mentioned here, here, and here. 2 is mentioned here, here, and here. And participant 4, like participant 1, only receives 2 partial shares. And like I said, our key bit length is 2, so our information rate for this scheme is now 2 over 3. This is a pretty big improvement over the previous one we got using the basic definition of information rate, which yielded 1 over 2. Now that we've defined the decomposition process we use to find the information rates of these graphs, we're going to define the methodology we followed to obtain the information rates of all of them. First thing we did was we had to acquire all of the graphs in a giant data table. We got it from this website and imported them to Mathematica in a .g6 format. The algorithm that we implemented decomposition construction in can best be described in 5 steps. 1, we found all complete multipartite subgraphs of the graph we were trying to analyze. 2, we found every combination of those subgraphs that added up to the original graph, and those would be our list of decompositions. We found every combination of decompositions, and we found the max bit length of key shares for each of those combinations of decompositions. We just iterated through that list and found the max L over R covering combination. And remember, L over R is the information rate. So what we are essentially doing is iterating through each decomposition combination and finding the information rate of that. Just to show you that it does indeed work, here's a graph of identical structure to the one we did in the last example with decomposition. And we get the same information rate with the same graph decompositions. So to test this algorithm, we decided to take a table of every graph with 7 vertices and treat them as secret sharing schemes. And the results were a table much too large to fit on this PowerPoint because there are a lot of graphs with 7 vertices. But there are 2 main types of results that were consistent throughout the list. 1, either the graph was already complete multipartite and so its information rate was 1, or 2, the graph was too complex to decompose, so we had to go with the lower bound of the information rate, which is again just the number of bits in the key to the number of max bits in a share. So what is the cause for these graphs being too complex? After all, we did see that the decomposition function worked fine on a graph with, say, 4 vertices. Well, remember that we had to find every combination of decompositions, and remember that decompositions themselves are the combinations of subgraphs. These graphs with 7 vertices can have dozens of complete multipartite subgraphs, and therefore hundreds of decompositions. And when you try to take every combination of a list of hundreds of indices long, you're putting too much strain on Mathematica's subsets function. As you can see, it can't even handle to find every combination of a list of length 40. You can't expect it to find every combination of a list of length 100. So all in all, what have we done? Well, the purpose of this project was to efficiently find the information rate of secret sharing schemes using graph decomposition. We tried to automate this process as efficiently as possible, and we did a fairly good job based on our results from 4 and 5 graphs. Once we got up to more complex graphs with 6 or 7 vertices and secret sharing schemes with 6 or 7 participants, we just found it was too complex and the algorithm completely failed due to computational complexity. That is the end of the presentation. Here are our references and resources. Please let me know if you have any questions.